Hello, everyone. I'd like to welcome you to our 4D Vision workshop. We are very excited to be running this workshop, which looks into 4D vision, visual understanding in 3D, but also taken in time. My name is Anelia Angelova, working at Google Research and Robotics at Google, and it's a pleasure to be co-organizing this workshop with Vincent Kasser from Waymo, Jürgen Sturm from Alphabet X company, Noah Snavely, and Rahul Sakhtankar from Google Research. We are very grateful to our invited speakers and panelists today, Raquel Urtasun, Marc Pollefeys, Davide Scaramuzza, Michael Ryoo, Thomas Funkhauser, Xiaodong Wang, and Drago Angelov. And very grateful to our program committee who have made this happen, and of course our participants, you guys, and the authors of the papers submitted. Just a little bit of a logistics. We have invited speakers, panel discussions with the Q&A, and panel discussion for the accepted papers. Please join our discussion. You can use the Q&A chat to ask questions, and then we'll ask them to the panel. And our sessions will be recorded, so make sure that you're muted and you don't have a camera, so that you are not recorded as well. And with that, we are off to our invited talks. And our first speaker is Marc Pollefeys, who is director at HoloLens Microsoft, and also a professor at University of Zurich. Marc, over to you.
Okay. Thank you to the organizers to having invited me. I will focus on going towards egocentric for the activity understanding for mixed reality. Before going there, I wanted to show a quick example of 4D videos and mixed reality, but then focus in on the actual topic. So here is actually a small example of how mixed reality and 4D videos can come together, and how in addition AI and translation technology can be used to have one person be able to project themselves at another place in the world, and at the same time actually use translation technology and text-to-speech with specific also matching the voice of the person, all of this integrated into a very nice 4D video in this mixed reality context. But what I want to talk about today, mostly what I want to focus on is essentially applications of HoloLens, where HoloLens is used in the real world, and looking at how we can leverage the capabilities of HoloLens beyond what is being done today, to assist people doing, potentially quite complicated tasks in the real world. So this is HoloLens. Why is it an interesting device for doing this type of things? Well, HoloLens comes with a lot of sensors built in. What you see here is essentially, of course, a color camera over here, but also head tracking cameras that allow you to track the environment combined with the MU. Also, up to 1 megapixel depth camera, which has two modes. You see two illuminators here, one for short throw, for being able at high speed to track hands and objects in the vicinity of the HoloLens, and then a long throw mode, which is for actually scanning the environment further out and getting the broader spatial context of the device. In HoloLens 2 also, in addition to that, we have eye tracking cameras with IR LEDs around here to help with eye tracking, and of course also microphones, etc. To be able to actually leverage this all in real time, be able to run all of these computer vision workloads continuously, there is also a dedicated chip that does all the heavy lifting here. You see here there's different cores on this chip that do eye tracking, surface reconstruction. This part here is actually more on the graphic side and for hiding latency. I hope you still can hear me. I saw there was some network issue. So that actually, because all the computer vision real-time processing happens on the front, on the processor there, which also preserves privacy. In the back, we really just have access normally to the APIs, the output of these computations, not the raw data, and we can run all the applications on an unencumbered processor. So what does HoloLens all do for us in the background with this vision chip? It does head motion computation, surface reconstruction, so it gets a lot of context for the user. Also, at the same time, it's actually possible to use that data to also do semantic labeling, for example. Here's a demo. This was sized so that it could actually be run in real time on HoloLens. So where you detect what's floor, what's walls, what's seats, tables, etc., etc. Okay. Now, in terms of user interaction, as I said, there's eye tracking built in. Here's a visualization of the system. This can, for example, be used to, help you as you read the text, know where you are, and therefore automatically scroll along. But of course, many more user interaction abilities can be built on this. It's also actually important to maximize the display quality by knowing exactly where your eyes are. In addition, these cameras can be used for authentication by reading your iris and therefore only replacing passwords and so on. Here's actually how this looks from the view of the camera. And you see here the glints that facilitate the eye tracking. Then beyond eye tracking, another new capability of HoloLens is that beyond just doing pinching motions and a few simple gestures, HoloLens 2 actually has fully articulated hand tracking. As you can see here, it's leveraging a combination of the DNN accelerator to find where the hands are, label the key points on the hand and the different regions of the hand, and then initialize from that tracking. And then the tracking is actually a geometric optimization, which you see at the bottom right here, which essentially leverages Marc algorithm doing the optimization. And so those two parts of the algorithm work in tandem and leverage the 45 Hertz depth camera signal that's coming in. Okay, so once you have all of this, you can do things like you see here. You see there is relatively low latency for the hand gesture tracking, and you see a slight displacement. That's actually due to the rendering to the mixture. If you are inside the HoloLens and you look at it, you will actually have a perfect alignment between your hands and the digital hands. So you see very intuitive and simple interactions with, in this case, the holograms. So with the digital information, we're not interacting at this point with the real world. Here's the combination. This video should show the combination of hand tracking, but also eye gaze. So here you can actually look at things and make them at these crystals and make them disappear, or do a number of other combinations of eye tracking and hand tracking. So great capabilities for actually interacting with digital information. But the question is, what about real world interactions? As here, for example, in the kind of Epic Kitchen data sets. So here we're actually manipulating, we're not interested in manipulating digital information, but we're just doing something, a task in the real world. And communities most interested about is actually being able to understand what a user is doing. Lots of work going on in that space. Here just a few examples of that, looking at the interaction between a human and its environment, the affordances, looking at interactions between hands and objects, contact points, etc., etc. So if we look at the context of mixed reality, are these type of interactions relevant? Indeed, they are. If we look here, we have this is one of the big value propositions for HoloLens. It's the possibility to call in a remote expert. So you have a person on site that has to do a certain complicated task, has to repair a machine that he's not an expert for, and therefore he needs help. Instead of flying in the expert to come do the job, especially in times of Corona, but also otherwise, it's much more effective if you can simply call in the expert, have the expert essentially look over your shoulders or look through the sensors on the glasses and see the same thing as you're doing. And that expert can give you these instructions, as you see here in the illustration, these type of 3D instructions that can be placed in the world in front of you to indicate what you should be doing. Okay? So that's one type of real-world interaction while wearing a HoloLens. And so obviously, one can imagine that if we can have HoloLens better understand what the user is doing, it could be quite valuable. Here's another scenario, is that for teaching people to carry out new tasks, like for example, a new employee, instead of having a person come over and teach that person step by step how to carry out the instructions, or provide people with a manual or how-to videos or so, it becomes a lot effective if you directly provide them with this type of mixed reality tutorial, just showing them immediately on top of the object, in front of them, showing the instructions overlaid on the world in front of them. Okay? So for those type of applications, it would be very important if, instead of having the user have to click step by step through the instructions, if HoloLens could actually follow along and be able to recognize if the user that's in training is actually carrying out the right steps or not. Also, generating those scenarios is actually a quite cumbersome and a relatively expensive task. For every task that you want somebody to learn through this mixed reality application, you actually have to step by step define, import all the right graphics, define like step by step actions and so on. And so one of the things we've been exploring is, can we actually simply record the expert using while doing the task, and then copy that over, essentially prepare from that, distill from that instructions that can be viewed as a, let's say, a how-to video on YouTube, translate that to a how-to mixed reality tutorial. But that becomes very cheap to generate by just recording the expert. So here's an illustration of that. So in the lab, the only thing we know how to make is coffee, and being in Switzerland is an espresso coffee in this example. So what you see here is essentially an overlay on the real world signal that the person is seeing, an overlay of these floating hands, which essentially are carrying out step by step how to make a coffee with this machine. And by aligning these recorded hands, by doing background subtraction, and then aligning these floating hands to the actual machine on which you're supposed to operate, you get a very simple and intuitive, mixed reality tutorial. Also, collecting this type of data can then be quite useful for then the next step, where we want to collect training data for recognizing different actions. Okay, so what you see here is some recent work that we did in the lab here in Zurich, where we tried to look at, in this case, RGB video, and then recognize actions from this. So in particular, what we do is we find the 6D object pose, we find the articulated hand pose, we recognize the action, and we recognize the object being manipulated. So all of this using essentially, in a first stage, a YOLO network that essentially finds the object and hand pose, object pose and hand pose. This is adapted from a 6DoF object pose network. And then this gets carried through a recursive neural network to then predict over the sequence the action that is being carried out. So here's the system in action. And as you can see, you see here both the 2D interpretation overlaid on the raw image that was used to carry out the inference. And then on the right, you see the 3-dimensional interpretation of the action. So this gave quite nice results. However, there's still a number of limitations. First, it's fully supervised, so it requires a lot of data with ground truth to train from. Second, the hand is just represented as a skeleton. requires also knowledge about the object, in particular the 3D bounding box of the object. So some work we did to try to go beyond that was follow-up work then with Yana Hassan, who was an intern in our group and worked with the rest of the team on being able to go to using full surface models for the hands, the manual model, and a detailed model of the object, and then try to learn also from a lot lower amount of data. So it's partly supervised reconstruction. So this is the model that we use here, and so in particular here we have both a common encoder and then a hand decoder and an object decoder predicting how those two interact. And here what you can see is how we can successfully drastically reduce the amount of needed supervisory data. In particular, we can go down to about 10% of the data with no noticeable difference, go further down where it's still qualitatively quite reasonable, but with some errors. If we go too far, of course, it all starts breaking down. As we go forward, we want to much more leverage HoloLens 2 directly as a platform for action recognition research. And in particular for that, we want to leverage the newly released or about to be released research mode. There is actually a tutorial on that. I'll say a little bit more in a second. So research mode allows you to capture some of the raw sensor streams from HoloLens. So this is not typically possible on HoloLens, and normal applications don't have access to this. But if you, as an academic, essentially want to do research, then we have a special mode in which you can put your device where some of the privacy constraints are relaxed, and where you can then capture some of the raw sensor streams. In particular, the short and the long throw depth measurements, as well as the grayscale cameras that are used for head tracking, as well as the IMU signal, which is something that's new now for HoloLens 2 that we also give access to that. What's nice is that while using these APIs for the raw sensor access, you can still, at the same time, leverage the hand tracking APIs, the eye gaze tracking APIs, and also the access to the RGB camera. So in other words, you now get a quite complete sensor suite that's available, plus all these higher level APIs remain available. So here's an example of research mode where we show that you have access to the IMU. I think the coordinate frame was put a little bit in the wrong direction, but what you see, the long signal corresponds to the gravity acceleration, plus, as you move, additional accelerations. So these are available, plus all these other, the fast frame, the depth camera for hand tracking, as well as the long throw at different frame rates. VLC are the visible light cameras, which are used for head tracking. Okay. Here's actually the hand tracking depth camera overlaid with the RGB camera in a very simple, naive way to just illustrate. And it shows you the type of things that you can capture live from the HoloLens. And as I said, at the same time, you would actually still have access to the fully articulated hand tracking results, for example. Okay. So here's an example of what you can really go to. So on the one hand, you can use all the data that's collected to have this background model as context for the action. You know how the device is moving through the world. This is the coordinate system of the device. You also, when the hands are into view, you can track in detail the one or the two hands. And the blue dot you see here, and the blue line actually also here, corresponds to the gaze direction. So all of this is available at the same time, as well as many of these raw sensor streams. So a quite interesting platform for research. Okay, so if you want to know more about this, there's a tutorial at the end of the week that will tell you everything on how to get access to all these data streams and how to use the tools that we have developed for letting you do this. And I also wanted to mention, as this might not be clear to everyone, but HoloLens 2 is actually available for sale now in the Microsoft Store and at other places in already quite some countries, and more countries are going to follow actually relatively soon. In addition to that, another way to capture interesting action, like get training data for interesting actions is to comes out of this project here, which is a project we want to do teleoperation of robots. And so we actually have through mixed reality. So the scenario is as follows. You get a person with a HoloLens, and the hand tracking of the HoloLens gets mapped to a robot, as you see here, or actually here in another example, where the robot and the person are in a different location. You actually see here 2 cameras mounted on an articulated arm. This is actually so that the cameras can be placed in the same position as the head of the person, and then the actions of the hands are mimicking. Okay, so the goal, this is the beginning of the project. This is a project done with my colleague Stelian Koros and his postdoc Roy Poran here at ETH, together with Microsoft. The goal of this project is to be able to do this remote manipulation, but of course the data that we collect is actually also directly could be used as training data for action recognition and for teaching a robot how to do actions. Now there's still need for high-end curated data sets, and here is some effort that's going on in the lab now by one of my students who mounted an Azure Kinect on a helmet. One of the key reasons is that we then have a number of other Kinects also being used, and we can hardware synchronize all of those streams. We can get like the full 30 frames per second from all of those different cameras. We can make sure there's no interferences by having offsets between the Kinects, and essentially have this type of data collections here. Some examples. The key being that we have these 4 streams, third-person viewpoint plus 1 first-person viewpoint, all recorded with these Kinects. Kinects have the synchronization pins, and so allow you to do this quite nicely. And here's some early results of that data set, where you see then from all this data, we can track the hands and the objects, and you see here the result of that, and then we make sure to curate this to avoid any issues with our ground truth data. Here's some more actions and some preliminary results here with our baseline method, which tracks 2 hands, the object and the action, all of this through YOLO networks and RNNs. So that was it. So in conclusion, there's important applications of action recognition in mixed reality. There's an opportunity to enable feedback during training. The HoloLens can both, once you can bring in action recognition, can in these scenarios where you have users being trained on a new action or being assisted, if HoloLens can follow along and understand the actions that are happening, it can essentially better assist the user. HoloLens 2 is also a great research platform. I hope I convinced you that it's a very interesting platform for egocentric action recognition. Beyond the RGB, you have access to APIs for hand tracking, eye tracking, head tracking, and environment modeling. And in addition, with research mode, you get access to raw depth sensor data, the stereo rig of 2 cameras looking forward, as well as the peripheral vision cameras and the IMU sensor data. So tons of sensor data available for supporting your research. And then finally, there's still a need for then these high quality sets, which is also something we work on with my student team. So that's it. Thank you. Okay,
thank you very much, Marc. That was great. Questions will be done in the Q&A session. And okay. Thank you. And our next speaker is Michael Ryoo. Michael Ryoo is an associate professor at Stony Brook University and a researcher at Google Research and Robotics at Google. He is interested in many topics and mostly in visual understanding and robotics and ego motion robotics. So Michael.
All right. Hello, everybody. Thanks for the introduction, Anelia. I'm Michael Ryoo. And today I'm going to talk about representing visual information in time. So to be a bit slightly more specific, I'm going to cover 2 different topics today. One will be about video representation learning, more specifically about how we can better abstract spatial temporal information in videos by building a new architecture. And we'll particularly be talking about multi-stream architecture. And the second topic today is about generative sequential models. And we present a model, sequential model, which is able to predict multiple possible future. And the name of this approach is adversarial differentiable grammar or adversarial generative grammar. And I'll try my best to cover this one as well. If I happen to, for some reason, run out of time, I will simply try to use this opportunity to introduce you the differentiable grammar and forward you to the live session 7 on Tuesday of the main conference. So first thing first, video representation running. If we want to represent or embed video data into lower dimensional representation, the first thing you will probably try to do is to first build a CNN with multiple convolutional layers and feed a frame, and then try to capture spatial information within the frame by feeding the RGB frame. However, video is not just one frame, single frame data, it's multi-frames. So you probably will want to also capture spatial temporal information by, first of all, using 3D CNN, doing 3D convolution, feeding a sequence of frames as an input. And when we talk about a video, often it is insufficient to just simply provide one single RGB modality as an input. It has been confirmed in many previous works that video often is multimodal, and feeding something as straightforward as optical flow, capturing motion information, greatly benefits the final video representation. And people also discovered not only the flow, but also sometimes just feeding RGB with different frame rate so that they become slightly different input modality also benefits the final video representation quite a bit. And we can also imagine that when we are talking about 4D vision, with multiple different sensors, the problem becomes more and more serious. And the main technical question here is, what would be the best such different multi-modality inputs? We can fuse it in many different locations. And what people discovered is it actually is beneficial to create multi-stream architecture for multimodal fusion. We create a CNN, a stream corresponding to RGB, and another stream responsible for taking RGB, abstracting flow, optical flow as an input. And people try many different ways of fusion, such as late fusion, early fusion, multiple hand design intermediate fusions. And again, the technical challenge here is, or the technical question here is, we actually have little understanding whether such fusions are good or bad. We empirically know that doing multiple fusions are good, having multiple streams is beneficial, but those are empirical findings, and all these were hand design. So, and as I am explicitly pointing out here, there are many possible connections, and we actually have a little guarantee which one's the best and which one's not. And this problem becomes even more serious if we start talking about just more than 2 streams. With 2 streams, you might be able to handcraft connections. With more than 2 streams, with multiple frame rate, multiple different inputs, such as like object segmentation information, you have little understanding how to connect. So the main technical questions, 2 main technical questions we are trying to explore with this particular work is, one, how should we connect? How should we connect what types of connections we should be having? And 2, how should we connect? And as mentioned, this is our main motivation behind AssembleNet and AssembleNet++. They are concepts which allows us to do neural connectivity search and learning. And I'll particularly focus on AssembleNet++, which will also be presented at ECCV later this week. And why am I emphasizing the connectivity so much, and why you should actually try to kind of consider the connectivity exploration is because if you actually benefit from such connectivity search, you are able to obtain quite a bit of performance boost. while still simultaneously using a comparable number of parameters. And surprisingly, the result I am showing you here on Cheray's dataset, AssembleNet++ didn't even benefit from any pre-training. So the standard practice when you want to actually do action recognition, video classification from continuous videos with hundreds or thousands of frames is to first of all pre-train them with a large-scale dataset like kinetics. But even without doing this, AssembleNet++ was able to meaningfully outperform prior models by a margin. So now let us try to look at how we actually do this. Before talking about AssembleNet++, let me first introduce you AssembleNet. It is a family of neural architectures which we obtain through the evolution. Our main idea was as follows. This is a super network, which shows you all possible connections between four-stream architecture. And the objective in our case was to find the optimal subgraph that maximizes the performance while maintaining the number of parameters. And each node in this supergraph is simply a convolutional block repeating 2 plus 1D or 3D residual modules. So this is your CNN architecture. This is the supernet, and you want to find the sub-network within this one. In terms of the connectivity, we actually connect using weighted summation so that we can actually learn the strength of the connection. So unlike previous residual modules, which obtain just one single input, now there are multiple possible inputs due to the connectivity, and we learn the weights. Actually, let me turn on the pointer. We learn the weights that tries to model the strength of the connectivity. And we also take advantage of dilated temporal convolution that dynamically controls the frame rate. And I will not go into the detailed procedure of how we actually search for such AssembleNet architecture, but I will briefly mention that this is a combination of log evolution and differentiable connection search. And it also just took one single day with a sufficient number of parallel workers, more specifically with 10 parallel workers. It only took like 1 day for the AssembleNet to find the reasonable architecture that connects multi-stream architecture in a meaningful way to obtain better video representation. So that was AssembleNet. And let me talk about AssembleNet++ in the aspect of how it actually extends AssembleNet to perform even better. So if we think about AssembleNet, what I try to kind of convince you is that it is about multi-stream architecture having learning different types of connections. And the connection learning was done using the weight learning for the weighted summation of the input. What we tried to add in AssembleNet++ was, first of all, confirm the power of such connectivity learning, not just with RGB and optical flow, but by also considering semantic object input, which has one more modality, input modality. And then we also wanted to explore a new way of fusing such multiple different streams, which we named peer attention, which actually means that your input is conditioned not just by yourself, but based on another block. So let me talk about the peer attention a bit more in detail. So self-attention, channel-wise self-attention, such as squeeze and excitation layers, will already be familiar to you. And if you look at channel-wise self-attention, it vectorizes the output from a particular convolutional layer, and then it tries to multiply. It does some fully connected layer operations, and it multiplies such attention vector back into the output of such residual convolutional representation as, and then that becomes the input to the next level. What we are doing is very similar but different. All we are saying is that now we not only want to make the attention to be done based on yourself, but based on different block, which means your output is being conditioned based on different peers. And here is the main motivation. The main motivation is that if we are actually very sure about certain object information in the input, then we can actually constrain the representations to look at certain things. So if you are very sure that there are like cooking instruments in the scene, then you can actually make your architecture to focus on the channels that correspond to the motion related to cooking and not related to other things like running and walking. We introduce one-shot differentiable architecture search algorithm in implementing such attention connectivity search. So there are many possible peers to take advantage of if we are thinking about the peer attention. And what we tried to do was to formulate this as a softmax summation of many different weights and then try to learn these weights to decide which peers would be most beneficial. So everything is differentiable if we formulate it this way. The main idea, as mentioned, is that we assign weights for each attention connections, and we take the softmax of all these weights, and then try to do the weighted summation based on such softmaxed weights. And this, very similar to many differentiable one-shot architecture search methods, will automatically allow you, by just training once, what your best peer would be to take advantage of. So once more, this was about connectivity search, and I'm showing you some results on Charay's dataset, as well as on another dataset, which is Toyota Smart Home dataset. Both these datasets contain continuous video having hundreds or thousands of frames, and this is an extremely challenging test. But AssembleNet and AssembleNet++, by looking at the connectivity, learning, it was able to perform quite reliably. And another thing we found throughout AssembleNet++ is that object segmentation information, although this is automatically extracted from using another black box CNN directly from RGB, is very beneficial to take advantage of. So connecting this to everywhere actually ended up being the best way to take advantage of object input. And we also show that such strategy of taking advantage of object connectivity as well as user peer attention is not just able to improve AssembleNet to become AssembleNet++, but is able to improve other different types of architectures like 2+1D CNN or 2-stream 2+1D CNN to perform significantly better than their backbone baseline architecture. So that's pretty much it in terms of my part one, talking about the connectivity search. And if you are curious about, if you want to know more about AssembleNet++, we have a poster session on Thursday, and please feel free to join the Q&A session of the workshop, and the code will become available at this website pretty soon. So switching the gear, let me also talk about the adversarial differentiable grammar. And this is a bit different. When I was talking about AssembleNet++, it was about representing video. We have a fixed video as an input. We were interested in how to best model the information in the video. The objective of a sequential model is a bit different. We are not just interested in representing video information, but we are also interested in predicting multiple possible future. From given the current state, we wanted to generate multiple future states. And this is an example. If you actually look at this example, the beginning, these two examples, the beginning part is actually identical, pitching and swinging, but after swinging, there could be multiple things that happens, such as a batter hitting the ball and running in baseball activity, or the pitcher pitching in again because the batter didn't hit the ball. And this actually suggests that after doing the pitching and swinging, the sequential model has to be in the bimodal state distribution, since it can go to two different things even after observing the same thing. And standard RNNs will have difficulty in handling such thing, and we wanted to do this. And the thing that came to our mind immediately was the formal grammar. For those of you who are familiar with formal grammar, you naturally will get the sense that this production rules in formal grammar, such as regular grammar, could immediately be used to model multiple possibilities by modal state distribution. So I am a bit running out of time. So let me try to use this opportunity again to introduce you what we are trying to do. So formal grammar was our main motivation. And what we tried to do was to emulate the behavior of a regular grammar with differentiable functions. So now we wanted to model terminals and non-terminals of a grammar representation as a vector representation. And we wanted to model production rules, which always has the form like this, as something like this, a recurrent unit with differentiable functions. To be more specific, we try to model the production rule with two different functions. One function trying to map a particular non-terminal, which is the state, to a set of production rules. And another function then selects a rule and maps a rule to a set of non-terminals and terminals. So here is an example. If we are talking about this particular production rule, what we want this recurrent unit to behave was as follows. Given the state B, we wanted it to consider 4 different production rules and assign probabilities to all these production rules. And using Gumbel softmax, we actually select, based on this probability distribution, one production rule and make it a selection vector that looks like this. And giving this to G, we wanted it to generate this output, the terminal B and non-terminal C like this. And since this is Gumbel softmax, it is able to select a different production rule and then generate different outcome. So, and of course, all the terminals and non-terminals will have a vectorized representation, making everything fully differentiable. So what are we actually trying to do? This is an implementation of a formal grammar in terms of differentiable functions. We are modeling terminals, non-terminals as vectors, and we are modeling production rules as 2 differentiable functions using Gumbel softmax to consider multiple possible future. You can also interpret this as a constrained version of a recurrent neural network, but with explicit hidden state branching. With Gumbel softmax, we are able to branch. And learning of such things would be very beneficial since people previously showed that use of the generative sequential models can be beneficial for things like model-based reinforcement learning for robots. And after trying this, we were pretty happy because with explicit branching, we were able to consider all possible sequences. However, consideration of such future sequences has a problem, particularly during the training process. In training, we don't know which future actually should be generated, and which, in order to make any of them actually match the ground truth and then measure the loss based on such thing, we actually need to generate all possible things. And this possible string sequence will grow exponentially, limiting, your training with computation and memory. That's why in this particular ECCV paper, we are introducing adversarial training of differentiable grammar. So instead of trying to enumerate through all possible generations, we just generate multiple things and then evaluate how likely it is using a discriminator. We don't try to match it explicitly with the ground truth. We just try to learn a discriminator function, trying to see whether the generated sequences make sense or not. So since I'm running out of time, I will not go into the details, but I'll just tease you that with adversarial grammar, we were able to obtain quite a bit of good accuracy, particularly when predicting longer time horizon future in human pose estimation or human pose prediction. And importantly, we were able to predict multiple different possible futures from a single pose. So starting from here, we were able to generate multiple different sequences corresponding to different actions, such as walking, eating, and sitting down. We also did this for future activity prediction. For example, instructional 50 salad data set, which is about making salad. And we were able to quite reliably, particularly compared to previous works, estimate what the future sequence will be given the current sequence. And we also apply this to charades and multi-tumors and obtain quite good accuracy. So that's pretty much it. And please let me know if you have any questions. For AssembleNet++, as I mentioned, we'll also be having poster sessions on Thursday. And for the adversarial grammar, we'll not only be having poster sessions on Monday, but there will be a live session on Tuesday, session 7. So thank you very much.
Okay, thank you, Michael, as well. Our next speaker is Davide Scaramuzza. Davide is a professor of robotics and perception at the University of Zurich and ETH Zurich. His research is at the intersection of robotics, computer vision, and neuroscience, and he investigates the use of standard and neuromorphic cameras to enable autonomous agile navigation, for example, of microdrones. He has received numerous awards, among which the IEEE Robotics and Automation Society Early Career Award, Google Research Award, KUKA, Qualcomm, Intel Awards, and European Young Research Award, and others. Davide, pleasure to have you. Over to you.
Thank you. First of all, maybe we can check the audio. Can you hear me well?
Yes.
Okay. So today I would like to talk about our recent work on learning vision-based agile drone flight. So flight is one of the most exciting locomotion principles, but also one of the most challenging. Birds are a big source of inspiration for researchers because they can navigate agilely in very complex environments, such as slaloming between trees, passing through narrow gaps, perching, and catching objects, which is what you see in this video. Now, what has been the progress on autonomous vision-based flight over the past decades? Actually, the research and development on vision-based flight can be traced back to 2010 within the European project xFly, which is the video on the very left. At that time, we used an onboard camera and the inertial measurement unit to achieve trajectory following completely autonomously. In this video, you see one of my PhD students that was actually safely making sure that the quadruped would not fly away by straining with a fishing rod, but the quadruped was completely autonomous. However, the speed was actually very limited. So the maximum speed was like 1 meter per second. And also the quadruped was not able to accelerate faster than a certain value, because otherwise it would lose completely the steady estimate. Then in the next 5 years, there was a DARPA project called FLA, or Fast Lightweight Autonomy Challenge or program, that actually targeted more agile or faster navigation. The target speed was about 20 meters per second, so 20 times more that than we achieved in the xFly project. However, the linear and angular accelerations were still limited. Then 5 years later, it's basically today, 2020, and nowadays we are lucky to have actually several products that can be bought that are able to perform some autonomous vision-based flight, DJI Mavic drones, as well as the Skydio R1 and R2. They are capable of reaching speeds autonomously up to 10 meters per second, so we're talking about 36 kilometers per hour. However, they still have a limited linear and angular acceleration, which is instead the goal of my research. How can we achieve very high speed linear and angular accelerations? So first of all, what do I mean by high speed flight, agile flight? Look at this video. This video was taken by a drone flown by a professional pilot. So just to be sure, this drone is not autonomous. Now the key question is, what does it take to fly as good or even better than a human pilot using only onboard sensing and computation? If you compare the performance of state-of-the-art autonomous drones with what human pilots are capable of doing, you will notice that there is a big discrepancy in terms of speed, versatility, and robustness. In fact, human pilots take years to acquire their skills that you see in this video. Which raises the question, can we build an alpha pilot that can fly drones as good or even better than human pilots? This is both my dream and also the goal of my research lab. if we will be successful, we should be able one day to demonstrate a drone that can beat the best human pilot at a drone racing competition or even perform acrobatic maneuvers better than human pilots. So maybe now you're wondering, but why are we interested in agile flight? Why bother? Well, you know, our goal as a community is to push the limits. And to push the limits, we need to work on really hard stuff. At my lab, we want to push the limits on vision-based navigation. And in my opinion, agile flight is one of the most exciting and hardest challenges of the next decade. In fact, in my opinion, I always tell my students, this is like the next moonshot. Because remember what US President Jeff Kennedy said in his famous speech on why we chose to go to the moon. What he said was, we choose to go to the moon, not because it's easy, but because it's hard. Because the goal will serve to organize and measure the best of our energies and skills. But beside pushing the limits, there are also practical and more relevant needs for agile flight. In fact, agile flight raises fundamental challenges for robotics research in terms of perception, planning, and control. Additionally, making drones faster will increase their range, meaning basically the amount of distance that they will be able to cover given their limited battery life. In fact, by flying faster, the drone can actually achieve more in the limited battery life. And this is actually key for search and rescue applications, inspection tasks, as well as for autonomous drone delivery applications beyond, that fall outside of the reach of GPS. So in this talk, I want to share with you one of our recent results done in collaboration with Intel, with a group of Vlad and Colton, on how to learn a control policy to perform acrobatic maneuvers completely end-to-end from sensory abstractions directly to control commands. As you will learn, the algorithms that we developed were trained only in simulation and were deployed onto a real-world platform without any fine-tuning. And by the way, our drone is fully autonomous and relies only on visual inertial sensors and onboard computation. This means that no GPS and no motion tracking systems were actually used. What you see in this video is a human pilot performing acrobatic maneuvers. Acrobatic flight with quadrotors is extremely challenging because it requires extremely linear and angular accelerations that push the platform limits a lot. As I said before, human pilots take years of practice to safely master such agile maneuvers. However, a tiny mistake can make the platform lose control and eventually crash, which is exactly what you saw in this video. Has there been previous work on agile flight? Yes, there has been previous work on agile flight. However, the main shortcomings were that they were either relying on near perfect state estimation coming from a motion capture system, or they were using onboard visual inertial state estimation, in which case, though, the performance was limited to very short maneuvers, like a couple of meters, and also was limited in terms of linear and angular acceleration. In this work, which is what you see in this video as the final result, we showed for the first time that a vision-based autonomous quadrotor that only has access to onboard sensing and computation is capable of flying acrobatic maneuvers with accelerations up to 3G, which is close to actually what the best human pilots can achieve today. In spite of the perception and control challenges that were raised by such accelerations, our drone could actually fly all maneuvers in a fast and reliable fashion. In order to achieve this, we trained an end-to-end sensory motor controller that directly regresses drone control commands from visual inertial measurement units. And by the way, our controller was trained exclusively in simulation. In fact, the advantage of simulation is that it is fast, it is cheap, and it is safe. And it does not require any human annotation. Additionally, it allows the collection of a large and almost unlimited amount of data in a limited time. For your interest, our training took about 4 to 6 hours on a normal desktop machine, but once completed, inference on board the platform only took 10 milliseconds. In this video, you see the real-world drone used in our experiments. So we use a custom-made drone that we made ourselves, whose overall weight was a little bit less than a kilogram, precisely was 900 grams, and has a thrust to weight ratio of 7. And this is actually more understandable for people who work in control and drones. But basically what it means is that we are exactly, we have a drone that is capable of performing the same agile maneuvers as those of professional first-person view pilots, so the ones that participate in drone racing competitions. It took a lot of time to actually miniaturize, everything such that we could achieve the same maneuverability in a drone that actually was also carrying, a computing platform to do autonomous and onboard perception and control. Our computer board was actually a Jetson TX2 that we used for neural network inference, while the images and the initial measurements were actually provided by an Intel RealSense T265 camera, which you see here. Now, when you control a drone, the classic approach to control a drone is to actually have first a state estimation, which means visual inertial odometry or SLAM, and then to control it. In contrast to the classical approach that basically rely on this separation of visual odometry and control, our approach instead directly learns end-to-end a controller in the form of a neural network. This controller maps from sensory inputs, such as images and inertial measurement unit readings, directly to control commands in the form of a collective thrust, so overall acceleration and body rates. So we are talking about roll rate, pitch rate, and yaw rate, if you're familiar a little bit with the airplane terminology. Now, the key question for us was what representation would be best for reducing the sim-to-real gap? Because remember, we are doing all the training in simulation. And for this, we actually used the results from a paper by Vlado and Colton and this group that was published in Science Robotics last year, which is titled, Does Computer Vision Matter for Action? In this work, what they do is that they benchmark different algorithms, and they try both to provide the network either images or intermediate representations, and then benchmark the algorithms in difference that go from controlling, for example, a certain player in a game, as well as, for example, controlling a simulated motorcycle that is trying to climb a certain cliff. And what they show, actually, the main conclusions of this paper is that controlled experiments indicate that explicit intermediate representations are actually better than learning directly from images at the current state of the art. They, however, point out that in the future, possibly end-to-end controller that directly infer the control commands from images may surpass the ones based on intermediate representations. However, based on these conclusions, we decided to opt for intermediate representations in order to reduce the sim-to-real gap. So in order to ensure this seamless transfer from simulation to the real quadrotor, we basically used appropriate sensory abstractions. By using such abstractions, as I will show later, the policy was actually able to generalize to different indoor and outdoor environments, as well as to different physical drones. Now, training a control policy purely in simulation and deploying it on a real platform, as we said, it means that we need to reduce this sim-to-real gap. What we show in our work, and you can read the paper if you're interested in the detail, is that the sim-to-real gap is actually upper bounded by the covariate shift introduced by the simulated and real observation model. The standard strategy to reduce this gap is to match the observation models, or in other words, to make the simulation as realistic as possible. In this work, we take instead a different approach. Instead of trying to match the observation model with an abstraction function f such that their Wasserstein distance decreases. Finding such a function, f typically requires domain knowledge since it is task or sensor dependent. In our work, the abstraction function f takes the form of feature tracks. So basically, we transform raw image streams into feature tracks, which we show transfer better between simulation and reality. One particular challenge of such an end-to-end approach was that the sensory input, so the feature tracks and the natural measurements, arrive at different rates. So to cope with this, we proposed an asynchronous architecture that can process inputs arriving at different frequencies. Concretely, what we do is that we feed the following features to the network. We feed the feature tracks given by a visual front end. Then we feed the integrated visual inertial measurements. And eventually we feed the reference trajectory. What we also do is that we keep a history of each input stream. And at a constant frequency, we take the newest batch of each stream and encode it using temporal convolutions. Then eventually, concatenating the encodings and feeding them to a standard multi-layer perceptron basically produces the control commands in the form of collective thrust and body rates. Now, in the experiments that I'm going to show, actually, we tried to answer these research questions. The first one was, how does the approach perform in comparison with a traditional pipeline based on estimation and control? The second one was, do intermediate representation eventually really favor learning and generalization as we actually postulated? And the third question was, what is the role of visual information and speed maneuvers? And eventually, can a network trained in simulation control a real platform? So in order to perform our experiments, we approached the Drone Racing League that on their website posts a catalog of trajectories that are really difficult to perform, even for human pilots. And out of these 25 trajectories, we actually took 4. These are the power loop, which is the one on the left, the barrel roll, which is the one in the middle, the mati loop, which is the one on the right, and a combo trajectories that basically combines all these 3 trajectories in one. All these maneuvers required accelerations up to 3G. Now let me jump to the results and then draw the conclusions. So we thoroughly evaluated our pipeline in simulation, and we show that our approach obtains results that are superior to a controller that is based on classical estimation and control, which is basically the top line, the one marked as VIO plus MPC. In particular, what we show is that with respect to traditional approaches for drone flight, based on traditional separation of state estimation and control, our policy makes the drone fly more consistently and precisely, while reducing the chance of a crash by up to 25%. So this is actually major. We also show that intermediate representations actually favor training and generalization. In fact, we also evaluate our policy with respect to a policy that takes directly as input images rather than our sensor abstractions. And we show that if you take as input all images, that it does not transfer at all to the real world platform. So this is actually key. Also, we also show that the longer the maneuver, the more important is the role of visual information. Actually see this in these results. Basically, what you can see by looking at the right plot, so you can see that, for example, if you used the separation of state estimation and control, actually the success rate is inferior to our learned control policy, which is the one in blue, which instead achieves a success rate of 100%. By the way, the success rate is calculated as the number of times that each maneuver could be executed without crashing. So using such abstractions, basically, we show that the policy, the learned policy, generalizes to different indoor and outdoor environments, as well as to different physical drones. Our drones, therefore, are shown to actually be more agile than was ever shown before, and indeed they are able to fly maneuvers which are extremely challenging, even for human experts. So in conclusions, the main takeaways of this talk are that simulation offers great opportunities to train robust sensory motor policies. Also, that simulation to reality transfer significantly benefits from abstract representations of the sensory measurements. And eventually that the longer the maneuver, the more important is actually the role of vision, because it allows us to overcome drift that accumulates over time. Thank you for your attention.
Thank you very much, Davide. We'll take questions later. Our next speaker, who will be a pre-recorded talk, is Raquel Urtasun. Raquel is the Uber ATG Chief Scientist and Head of Uber ATG Toronto. She is an Associate Professor in Computer Science at Toronto University and co-founder of the Vector Institute for AI. Has received multiple awards, for example, the NSERC EWR Stacy Award, NVIDIA Pioneers Award, Ministry of Education and Innovation Early Researcher Award, and many others. And I will share screen. And
hi everyone, my name is Raquel Urtasun and I'm the Chief Scientist at Uber ATG, as well as a professor at the University of Toronto. In this talk, I'm going to review the latest work that we have done on interpretable neuromotion planners. A very popular approach in academia to autonomy is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, for example, LiDAR or images, and the output is the information necessary for the self-driving car to drive, for example, steering command and acceleration. The advantage of such an approach is that it is very easy to get a prototype with just a few lines of code. Furthermore, the system is trained for the end task, which is the task of driving. However, this paradigm has several key disadvantages. It is difficult to incorporate prior knowledge, and thus make the system respect the rules of traffic. It also has no interpretability, which poses a problem for the system's validation and safety. An alternative is the traditional software stack, which is composed of a set of modules executed one after another. Every fraction of a second, the vehicle senses the environment. This is illustrated here with a bird's-eye view of the LiDAR point cloud. The first task is then to localize the vehicle with precision of a few centimeters. This is done not only to route the vehicle to the desired destination, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene, here depicted with rectangles for vehicles and circles for pedestrians. The prediction system then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. Then the motion planning module focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as friction and simplistic vehicle dynamics. This full process is then repeated every fraction of a second, typically every 100 milliseconds. The advantage of this approach, or this type of paradigm, lies in the fact that we have interpretable intermediate representations, and it is easy to incorporate prior knowledge. However, reaction time is typically large as computation adds up. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Furthermore, the different models are not trained for the end task, and thus improvements in model performance do not translate to better driving. Our vision, which is different from any other competitor, has the advantages of both end-to-end and traditional engineering approaches, but without inheriting the respective drawbacks. In particular, we believe in having a single AI system that can automatically adjust itself to any changes, thus increasing significantly developer productivity. As computation is now shared across modules, the resultant reaction time is also much lower. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge, for example, to guarantee that we follow the rules of traffic. And finally, since our approach is trained for the end task, every improvement results in better driving. Our first attempts towards this vision focus on developing approaches that can do joint perception and prediction. That is 2/3 of the software stack with a single AI algorithm. Fast and Furious was the first such approach that appeared at CVPR 2018. The input is a history of previous LiDAR sweeps. Using the pose of the SDV at different time steps, we can project past sweeps to the current coordinate frame. We can then voxelize the point clouds into a bird's-eye view tensor with 4 dimensions: height, width, time, and depth. Now we can run 3D convolutions using depth as features to fuse the spatiotemporal information. Once the time dimension has been reduced, we can predict the output with 2-dimensional convolutional headers. For each pixel in the output map, we can predict a classification score and a series of future waypoint regulations. To obtain the final detections, we threshold the scores and apply no-maxima suppression. We then obtain a single feature trajectory for each actor by indexing the regression tensor at the positive locations of the classification after NMS. In this video, we show the LiDAR point cloud together with the detection scores, bounding boxes, and the short-term motion forecast for 1 second into the future. The vehicles are color-coded according to a heuristic tracker that matches detections to previous motion forecasts as a post-processing step. You can see here how difficult is the task of driving, where we need to localize very accurately a very large number of traffic participants, all in a fraction of a second. As a disclaimer, I'm going to give a full talk at a different workshop on our efforts on joint perception and prediction. So I point you all to look at preconditions in the future for more information on this. However, in the following, today I'm going to talk about interpretable neural motion planners, which is the future of where we see autonomy going. I will present 3 different efforts in this direction. Our first work is the end-to-end interpretable neural motion planner published at CVPR 2019. It uses a deep neural network to produce a learned cost volume and improves the performance of the deep network with auxiliary detection and prediction tasks. Later, we proposed DSDNet, Deep Structured Self-Driving Network, which further improves performance and interpretability, but outputting non-parametric multimodal predictions and planning condition on these predictions. The third work investigates how we can bypass detection post-processing, which may lose useful information. We propose perceive, predict, and plan, safe motion planning for interpretable semantic representations, where we replace instance predictions with an instance-free semantic occupancy representation and use learn interpretable planning costs over that to produce planning. Now, let me briefly explain the main idea behind each of these approaches. The end-to-end interpretable neuromotion planner is our first attempt towards this direction. It takes LiDAR and an HD map as input and jointly outputs detection, prediction, and planning results. For planning, the model produces a learned planning cost volume, which will then be used to generate a planning trajectory. As you can see on the top right, the learned costs can nicely navigate our ego car to follow the lane and avoid collision with other cars. Let's have a look at how the model works. The input to our model is raw sensor data in the form of LiDAR point clouds and an SD map, which are fed to a CNN in order to extract useful features. To produce interpretable representations, our model outputs detections on predefined anchor boxes. It also predicts each actor's future trajectory simultaneously. Next, we conduct planning. The model utilizes a simple deconvolution network that takes the backbone feature map and outputs a cost volume. The value of each pixel in this volume represents the cost for the ego car to be at that location and future timestamp, where different timestamps are encoding with different channels. Of course, lower cost regions are preferred. Here we highlight a low cost region in green. The purpose of this volume is to find a low cost planning trajectory. To see how it works, we show a zoom-in view of this volume. Again, different channels encode the cost map in different timestamps. And for an arbitrary trajectory, its cost can be easily computed by first indexing the volume at the appropriate temporal and spatial locations, then summing them together. During inference, we use a physically valid trajectory sampler to sample a wide variety of trajectories. These trajectories are guaranteed to follow vehicle dynamic constraints. We then evaluate the cost at each trajectory using the cost volume, and select the minimum cost one as our final planning output. Importantly, all computations from raw data to the final trajectory can be done in a few milliseconds. We train our model end-to-end with a multitask loss, including detection, prediction, and motion planning losses. For detection and prediction, we use standard classification and regression losses. For planning, since we do not have ground truth supervision for the cost volume, we utilize imitation learning and encourage trajectories to have low cost if they are close to the expert demonstrations. We also penalize trajectories that collide with objects or do not follow traffic rules. We evaluate our approach in our challenging ATG40 dataset. This dataset contains over 1 million frames from more than 5,000 snippets collected from multiple cities across North America. It provides plumb clouds from a 64-beam LiDAR sensor and high-definition maps. It contains very challenging urban scenes with many actors, making it interesting for interactions. Here we show our results. Compared with the state-of-the-art, our model achieves on par or better detection and prediction performance at the time of publication of the paper. More importantly, as we can see in the figure, our planning results have a much lower collision and line violation rate, which indicates safer planning. Let's look at qualitative results now. Our model takes LiDAR and HD maps as input and outputs detection, prediction, as well as the motion planning cost volumes. We highlight low-cost regions for different time steps using different colors. Our planned trajectory is shown in red, and the ground truth trajectory is shown in blue. As we can see here, it follows the lane perfectly. Note that our cost volume captures multimodality. In this case, we can either go straight or change lanes. When approaching an intersection, we can either keep lane or turn right. We can also handle blockage. The cost volume shows a preference to lane change in order to avoid collision. Here are two examples of super nudging in heavy traffic, which is a very complex maneuver to do in self-driving vehicles. As shown in MMP, sharing computation among all three tasks allows us to perform full inference within a few milliseconds and also maintain interpretable intermediate representations. However, there are still two major weaknesses of this work. First of all, the future is at times very uncertain. For instance, for the highlighted car, this car could either turn right or go straight. Moreover, different actors interact with each other and follow traffic rules, such as yielding and not colliding. Therefore, a multi-agent prediction with calibrated multimodal uncertainties is necessary for safe planning. Second, although NMP is able to predict the future, its planning model is not explicitly conditioned on the prediction output, which may cause some inconsistencies during the planning and the prediction models. To address these limitations, we propose DSDNet, a deep structured neural motion planner that jointly reasons about perception, forecasting, and motion planning. Specifically, our method has several advantages. First, computation is shared between models. Second, our method explicitly models socially consistent multimodal uncertainties in the future trajectories of the traffic participants. And finally, our learning-based planner leverages the power of deep learning and takes traffic rules into consideration, as well as in order to guarantee safety. Now, let's have a look at how our model works. Given later point clouds and an HD map as input, as before, we have a neural network to produce backbone features, which will be shared across all our models. We first use these features to predict detection results. For example, here we have 3 vehicles that have been detected. Our next step is to predict the future behaviors of all actors, as well as their uncertainties, which are shown as colorful regions in the figure below. Here, different colors mean different future time steps. Predicting these uncertainties is not a trivial task, as we expect to predict a multimodal non-parametric distribution which can capture complex situations. More importantly, the behavior of all actors should be socially consistent. For example, they should not collide with each other. To have an efficient representation for this non-parametric distribution, we first sample a set of dense, diverse, and physically feasible trajectories for each actor, and then build a probability distribution over these trajectories. More specifically, we use a neural network together with the backbone feature map to predict a unary energy for each trajectory. After normalization, these energies will provide us with a probability distribution. By doing this, for each actor, we have an estimate of the future. However, the produced probabilities do not guarantee socially consistency, as shown in the red circle, and it is hard to encode human knowledge, such as avoiding collisions, within our deep learning-based framework. Therefore, in order to model these interactions, we model each object as a node in a probabilistic graph, and have the edges encode our knowledge about their interactions, such as collision avoidance, yielding, etc. For example, for every pair of actors, we can evaluate a pairwise energy. In this case, since the actors' actions are socially consistent, we have a low pairwise energy. In contrast, here we have high pairwise energy since the actors collide. Then we conduct an inference process using loopy belief propagation so that high energy in consistent scenarios have overall low probability. Finally, our model plans a safe trajectory for the ego car by considering the current situation and other actors' future behavior. Similar to NMP, we formulate planning as a cost minimization problem and solve it by first sampling trajectories, evaluating the cost of each sample, and then picking the minimum cost trajectory as our planning output. To compute the cost of a given trajectory sample, we also use a neural network to evaluate its unary cost. For example, an out-of-road trajectory will have high cost. However, this learned cost does not fully utilize the benefits of our predictions. Instead, we hope that planning can explicitly minimize the expected collision rate given our prediction results. Recall that our predictions are given as distributions over discrete trajectories. Therefore, we can easily compute an expected collision rate using a weighted sum. As shown here, the pairwise cost will be high if an ego trajectory collides with other actors, and low if it does not. Finally, we combine unary and pairwise costs and find the minimal cost trajectory among all samples. This gives us our final planning output. Here, we first report our prediction performance. We compare our multimodal socially consistent prediction method against several state-of-the-art methods on a number of datasets. Here we show results on two publicly available datasets, Nuisance and Pre-Carla. We achieved significantly better prediction error. Our method also achieves a near zero collision rate among predicted trajectories, which corresponds to more realistic human behaviors. Here we show our planning results. Again, we compare against an end-to-end imitation learning method, as well as our previous NMP method. Our DSD approach achieves significantly better performance in terms of collision and lane violation rates. This is due to the fact that now our model explicitly considers multiple future possibilities, and then plans a safe trajectory that is compliant with other actors' future behavior. Now let's see some qualitative results. In this figure, each blue box represents an object, and its dotted line represents its most likely future prediction. We visualize the model's uncertainty estimates with a dense color map. Different colors represent different times. This is the uncertainty at 1 second into the future. This is 2 seconds into the future. We can see that our predicted uncertainty becomes more spread out as the future is more uncertain. Here is 3 seconds into the future. Our algorithm is able to capture all the possibilities for the car approaching an intersection. This is a good thing. It suggests that our motion planner will take all possible features into consideration when planning its trajectory, not just one, as before. Here is one more result of motion forecasting. We can see that for far away and turning objects, we are more uncertain of their future. On the other hand, for objects that are going straight along the lane and close to us, our model is quite certain. Next, let's see some planning results. Here we show a scenario in which our ego car follows a curved lane very well. This is a turning scenario. Here you could see that our planned trajectory is smooth and follows the lane structure very well. This is a situation in which a parked car blocks the ego car lane. Thus, our planner nudges around the parked car to avoid collision. Here's a short demo. As you can see, our model nicely captures multimodality, especially for vehicles that are approaching an intersection. When a vehicle is driving on a straight line, our model is more certain about its direction, but a bit uncertain about its future velocity. Here's an example where we perfectly predict that the leading vehicle is stopping, and we plan a nudging trajectory to avoid collision with the parked car. This shows that our model can follow the lane perfectly. So far, we have discussed two efforts on how to improve interpretability for end-to-end neural motion planning. Both of these works detect surrounding actor first, and then conduct planning based on detection results. For example, in this case, the self-driving car situated in the bottom will know a coming vehicle is crossing its left turn lane, and thus will yield to the car. However, detection requires post-processing and only reflects an actor if his detection score exceeds a certain threshold. But if the detection score becomes below that threshold, and then what happens when the ego car misdetects the vehicle? This might cause a severe collision, which of course we don't want to see. We tackle this issue by designing a novel end-to-end approach that perceives, predicts, and plans. The overall idea is very simple. Rather than performing object detection and then predicting trajectories for each object, our model directly generates semantic feature occupancies. Furthermore, the occupancy forecasts are scene-based and instance-free, and hence our approach does not require thresholding of detection scores or performing NMS, thus increasing safety. The planner uses these non-parametric spatiotemporal occupancy maps along with other interpretable costs to plan a trajectory that is safe, comfortable, and respects traffic rules. Note that the entire model can be trained end-to-end since all the components are differentiable. Let's dive a bit deeper into the exact intermediate representations we use. We consider vehicles, pedestrians, and bikes as the classes we want to predict their occupancy. Note that it is easy to extend this to other classes in the future. To make the representations more interpretable, we should devise them semantically as shown in the hierarchy. For pedestrians and bikes, we only differentiate between visible or partially visible, meaning that there are one or more leader points on their surface and occluded. For vehicles, we should divide them into park, on conflicting lane, oncoming traffic, on the route, occluded, and others. This subdivision allows us to learn different weights for the motion planners of cost, corresponding to different subcategories. For instance, we do not need to keep the same safety buffer if we know a car is parked than if a car is in a conflicting traffic. Note that we assume vehicles, pedestrians, and bikes to be independent, since we can find cases where a small region of space is occupied by more than one class. For instance, a pedestrian getting out of a car. The subcategories within each root category are considered mutually exclusive. In the drawing, the colors of the occupancy represent their semantic class. We represent two pedestrians that are visible, a car that is on the route, and a car that is on a conflicting lane, and a visible bike. Similar to previous methods, we take a history of voxelized LiDAR strips and a raster map of the scene as input. We extract LiDAR and map features with a two-stream CNN and fuse them by concatenating them and adding a subsequent CNN. Finally, A recurrent occupancy update predicts the semantic occupancies into the future. As you can see, there is no, there is no processing at the actor level. This is another advantage of our method, since the computational cost does not increase in more cluttered scenes, which is important for real-time applications like ours. Let's dive deeper into the recurrent occupancy update. To obtain smooth occupancies over time, we leverage a special memory and a CNN-based update that only predicts the residual with respect to the previous occupancy. The planner samples a set of trajectories. A cost function is used to evaluate each trajectory considering different aspects of driving. The best trajectory is then selected for execution. The spatiotemporal occupancy maps are used to penalize trajectories that overlap potentially occupied regions. We use the map data to, for example, penalize trajectories that are not close to the lane centers or violate boundaries. Another aspect of driving that is included in our cost function is the route. Trajectories that are moving towards the lanes that eventually diverge from the route are penalized. We also take into account the smoothness and comfort of the trajectories in the cost functions. For example, trajectories that are turning at higher speed will cause large lateral acceleration and are not pleasant to the rider. Such trajectories get penalized as well. So as you can see, the trajectory cost function in our planner considers various aspects of driving. The relative importance of these subcosts are learned jointly with the rest of the pipeline. Here are some quantitative results for open loop experiments. That means that we enroll the predictions and a motion plan for 5 seconds into the future without replanning. In other words, in these experiments, the SDV does not get any further observations within the future horizon of these 5 seconds. We compare our method to ACC, which is a car following model. Imitation learning, which directly outputs the ego trajectory from the fused feature volume in the model, and the neural motion planner that we were talking about before. We also include a model that detects objects and predicts multiple trajectories for them that are explicitly used in the planner's cost function. The results show that our proposed model is much safer than the baselines. For example, we get 40% less collisions at the best baseline throughout the 5-second future horizon. Once again, these are open loop experiments where the SDV does not get observations during the 5 seconds interval, and the rest of the actors do not react to our actions. Also, the generated trajectories of our model are more similar to the driving behavior of humans. Here is a video that shows examples of predicting semantic occupancies and open loop plan trajectories. The semantic classes are color-coded according to the legend on the top right. The empty boxes indicate ground truth objects and SDV. Our model is able to capture multimodality of future occupancies caused by each vehicle. The generated trajectories avoid occupied regions and stay within the lanes. The model is also able to pick occluded regions indicated by cyan color. Let me play this for a little bit so that you can observe more scenarios. And in here we are doing pedestrians, cyclists, as well as vehicles. The previous results are from open loop experiments, meaning that the current self-driving vehicle plan does not affect the world in future timestamps. To evaluate the closed loop performance of our method, we use our in-house simulator, which we are observing here in the video. Our closed loop simulator leverages our own state-of-the-art LiDAR simulator, LiDAR-Sim, that has just been published at the CVPR, and that you can see as an oral section during the conference. The simulation loop runs at 10 Hz. In each iteration, first the LiDAR sensor is simulated to generate a point cloud. Then the autonomy model plans a trajectory using the generated point cloud on the map. And finally, the state of the world is updated based on each object's planned trajectory. Note that the actors other than the SDV can have their own trajectory planning logic or use a predefined trajectory that is not reactive to the environment. The video that you were showing showcases an example of this closed loop execution, where we can see that the vehicle is basically ACCing to traffic. We then run 80 challenging scenarios, each for 10 seconds duration with our closed loop simulator. Each scenario has a subset of the yellow vehicles shown in the left image. These vehicles are initialized at various speeds and starting locations that are in conflict with the SDV route, particularly designed to test the safety of our decision-making when facing critical situations. Furthermore, they are not reactive to the environment and hence non-compliant. We collected various planning metrics as shown in the table. We compare our method to a method that detects objects and predicts trajectories. The results show that our end-to-end planner is much safer and generates significantly more comfortable trajectories. To summarize, we have explained how we can learn end-to-end motion planners that can directly output trajectories directly from the road sensor data with intermediate representations for perception and prediction. This enables shared computation among the different tasks of the autonomy pipeline and ultimately decreases the reaction time of the SDV. Moreover, we show that our models can plan trajectories for the ego vehicle that are consistent with the predictions for the other agents in the scene by taking this into account in our motion planning costs. On top of that, we propose an instance-free semantic occupancy representation that avoids information loss between perception and downstream tasks by removing the need of discrete decisions such as thresholding or NMS in object detection. Finally, we have shown that we can still make use of interpretable cost functions in the planner that encode our prior knowledge about driving and are interpretable. This is an extremely exciting direction of research, and I hope that many of you will be working on this in the future. Thank you.
Welcome. So I'll lead the paper spotlights. So we have the corresponding author here. We have 2 papers in this AM session and 5 in the later session. We're a little bit late, so we'll make this very quick. Let me check. So, Sure, are you here?
Yeah, I'm here.
Awesome. Perfect. So I can present your slides. So the first paper is 4D forecasting, sequential forecasting of 100,000 points. Take away.
Okay, thank you for the introduction. This is Xinshuo from Carnegie Mellon University. So I'm going to talk about 2 works. This first one, 4D forecasting. So this one we have two key contributions. The first is a new perception and prediction pipeline that inverts the order of forecasting. So look at in the conventional pipeline that people often do detection, tracking, and then forecasting to get object trajectory in the future. But in our new pipeline, we first forecast the sensor data, specifically the point clouds, and then run detection and tracking on top of the predicted future point clouds. So to support this new pipeline, we also propose the new forecasting task, which is the first step, sensor data forecasting that predicts the future data point clouds. That's it for this work. Thank you.
Awesome, thank you. Next one, also you, will be graph neural networks for 3D multi-object tracking.
Yeah, so this work, specifically we do 3D multi-object tracking using graph neural networks. So I'll show a screenshot of the results that has these color 3D bound boxes. Each one is a single object that's been tracked by our system. Unfortunately, I cannot put a video here somehow. But if you are interested, there's also a demo on the ECCV platform you can visit. On the right, we demonstrate key ideas of our work. So the key components is shown down in the middle, the feature interaction. This is the one that's not appeared in the prior work. Specifically, we use graph neural networks here. The idea is to use this feature interaction to encode context features from other objects. This is done by aggregating neighborhood object features. And so the relative features of other objects can be encoded for each object, which can hopefully improve the data association to improve the discriminated object feature learning for data association. Thank you. That's it for this work.
Awesome. Thank you. Yeah, so this is the time for a quick question from the audience. Otherwise, we have some questions. So for this work, maybe one question will be how you handle occlusion and disocclusions when you do prediction of the point cloud.
Specifically, we don't do explicit occlusion handling in this work. Because of the data that we received is LiDAR point cloud, so there's already a lot of occlusions for sure, right? Because the LiDAR sensor is essentially a 2.5D sensor that cannot capture all the points of objects. Some points are behind behind some other things will be occluded. So the input data will be included, and we cannot really correct for it. So the output data will be also in the same manner. Basically, we just forecast the data. We just forecast the point cloud from what we can see, but not from what we cannot see.
I see.
Yeah.
And do you see any problems with deformations when you predict the future and the detector working like suboptimally on these predictions?
Yeah, we observe a lot of problems. So the first one is the predicted future point cloud data is not that sharp. It's kind of the common problem in point cloud reconstruction, but like very severe in our situation because we are doing point cloud prediction or reconstruction for the entire thing, right? Like most prior work just doing for a single object, but still like for example, the thing that we reconstructed and also the object point cloud we reconstructed also like a lot of them has like a very smooth shape. So it doesn't really look like a real object, a real building or something like that. But something interesting is that even with that kind of smooth shape, if we train a detector on top of it, it can still detect the object stably. Although not achieve the same performance as you have a detector on the standard, like the real LiDAR point clouds. Yeah, but there is a big domain gap there, I think.
Thank you. Then very quick question to this work, very quick. So here you do the multimodal fusion. I think this is a light fusion in your work, right? Do you have any experiments on like earlier fusion to make the feature extraction and multimodality even more?
I do have a ablation on that, but I think it's not possible to show here, right? If you want to learn about that, like we have the full papers in CVPR 2020, which has that experiment. So basically, we demonstrate that if you use multiple modalities instead of just one, you could get more stable results. I kind of run different experiments that you use each individual modality, and they use 2 of them in different combination, and they use 4 of them, like all of them basically. So you can see the performance showing the full paper. Yeah.
Awesome. Thank you very much. These are great works. And with that, I'll hand it over to Noah to lead the panel discussion.
This is so cool. Can you hear me?
Yes.
Yeah, okay, this is great. Okay, so yes, thank you everybody. Let's see, so we'll have a staged panel. I think we're gonna try to end on the hour. Well, first of all, let me introduce myself. I'm Noah Snavely. I'm a faculty member at Cornell Tech here in New York City, where I'm dialing in from, and a researcher at Google Research. And we have 3, well, actually, well, I see Michael's still here. Is Michael, are you also, let me just, well, I see 4, there might be 4 people chiming in. So let me introduce them really quickly.
It seems that, I will be joining the afternoon panel session discussion.
Okay.
Yeah, but, I'm here just to, listen to what you guys talk about.
Okay, I think that also means that if someone has a question for Michael's talk, they can also chime in. This will be a slightly combined panel plus Q&A. I see. So just to lay the ground rules, if you have a question from the audience, please type it into the Q&A. I see a few questions held over from the talks, which I will get to. I think they're both for Raquel. But I'll start with a few questions. So I just want to briefly introduce the panelists. You heard from them already. But in case you're joining now, we have Raquel Urtasun, who is we have Raquel Urtasun, who's the chief scientist at Uber ATG and head of Uber ATG Toronto, and a professor at the Department of Computer Science at the University of Toronto. We have Marc Pollefeys, who's a director at Microsoft HoloLens, as well as a professor at ETH Zurich. And we have Davide Scaramuzza, who's a professor of robotics and perceptions in informatics and neuroinformatics at University of Zurich and ETH Zurich. So we have, we also have Michael Ryoo, who I guess will be a surprise guest panelist in case people have questions for him. He'll also be at the afternoon session. We have our esteemed panelists here. And just to set the stage, this workshop's about 4D vision. I think a lot of vision people are used to thinking about the 3D world where like you have nice tools like geometry. And then vision people are also, a lot of people are into video analysis where you think about it as pixels over time. But I think there's a lot of interesting work that can happen at the intersection of those two. So where you're understanding the world in 3D, and it's important to take into account the temporal nature of the world. And the way I think about it is, robotics and AR and VR, where you're understanding a scene unfolding in front of you with moving objects is one aspect of that. But, time operates at different scales. There's also things like illumination happening over the course of a day. There's changes to the environment itself over, years, like buildings get built. So I think all of these somehow get folded into, at least my view, 4D vision, anything that has to do with the temporal nature of the world. So, people like in communities like robotics think about this all the time, but again, in vision, this is something we're maybe not as used to thinking about in terms of like 4D understanding of the world. So I'm excited to talk to our esteemed panelists, and I thought, okay, I'll just start off with a question. And again, please type, as an audience member, type your question to Zoom Q&A. So I thought I'd just start by asking, okay, so where are we as a field? So if we want to have computer vision algorithms operate in 3D and in dynamic scenes, how close are we to having systems that can do that? Are there problems that have been solved, or tasks that systems are doing all the time now? Or if not, what are the big challenges you see in this area? So let's see. Does anyone want to chime in first? What problems? Yeah. So, are there tasks that have been solved? Like, where are we in this field? Marc, do you have any thoughts on this?
Well, I think so I think a lot of at the algorithmic level, a lot of things have been done at different timescales, as you say. So you have things like slow-moving things like change detection, detecting if one 3D model is the same as the other one, look at the discrepancies, figure those things out. But then, of course, as we've seen today, both with Raquel and also in self-driving cars and in action recognition and so on, there you really have intrinsically dynamic environments. There you're truly 4D with, of course, one dimension being a bit special because it only moves one way. I think the challenge, like one practical challenge I think we all have with these type of things is just the amount of data and the fact that it's temporal, that it goes in one direction. But just the amount of data makes it practically harder to do a number of things, to work with it. And so our models still are often simpler than we would like them to be. And I think also the fact that in space there are natural neighbors, there is spatial continuity and so on. In time, you already need to do computations to find like the kind of correspondences to be able to do a lot of meaningful things. So I think those are some of the challenges that I would see.
So if I can maybe chime in on what Marc said. So let's see. So I think there's been a lot of great progress in the field in the past couple of years. Particularly, I really like the line of work of combining classical approaches with deep learning, right, to get the best of both worlds. I think is very, very exciting. Not forgetting about the physics, not forgetting about the geometry, but at the same time learning the things that are difficult to model. However, that being said, right, for when you want to actually build systems and deploy them in the real world, there is so much more to be done. So there's still definitely a lot of juice to squeeze there. And I think what is, one thing that is very interesting, at least in the solar driving field, is that, these 4D sort of perception algorithms are getting very good, right? You look at, the videos, whatever, it's very impressive, the level of performance that we are at. But what is interesting is that, improving your perception algorithm doesn't imply that you actually drive better in the case of self-driving. And that between the end task and the perception system is so important. And I think this is, one of the remaining open questions into how you actually, do so. In our case, we are looking at end-to-end approaches, and I show you today 2.5, I guess, since the video was cut in the middle. But I think that's, the same for, drones, the same for other VR approaches. I think it's a very, very exciting direction.
Davide, maybe I'll ask you, have we solved drone flight? I mean, you're like, okay, so is the 4D perception we need for drones good enough, or there's still, what has been solved? What still are the big challenges there?
The quick answer is it depends on the speed and on the task. So if you just want to do, for example, moving in an elevator-like fashion, like, back and forth on a street at a given speed, then this is already solved, okay? So we could already do that with the first visual slams 10 years ago. Instead, if you want to do things more agilely, but also at higher speeds, then we have different problems. The first one is robustness. So basically, you have algorithms that can be deployed in the wild. And the other thing is generalization also to different type of environments. So here we are experimenting with combining, as Raquel said, both geometric-based approaches and deep learning-based approaches. In the work that I presented in this workshop, actually, I did not present those because I was excited to show that we can also learn a control policy directly in simulation. There is a bottom line though, sorry, a bottleneck though, which is the fact that still the standard classic control architecture that relies on the separation of state estimation and control will be able to generalize better to different type of trajectories. While instead, we still, using only end-to-end learning, we will still have to retrain exactly for each specific trajectory. So this has to be done. Then I was talking about agility. So what I mean by agility, as I said in the talk, is basically to do maneuvers that are that show very high accelerations, both linear acceleration and angular acceleration, very much like human pilots. Because this is a key actually to allow them to be able to perform things, also fast. Think of search and rescue applications when you want to save the battery life. So if you move faster, then of course you can do things you can improve the range of drones. But then here we have also problems which have to do with detecting obstacles and other entities as fast as possible, meaning reducing the latency. So I did not talk, actually I resisted from talking about event cameras in this talk, but actually event cameras there provide a lot of opportunities. To actually complement what Marc also said, basically, standard cameras sample the scenes usually at 30, 50, or even 100 Hertz, while event cameras can allow you to have a more continuous sampling of the scene. So you have basically more information. More information, of course, also means that you need a faster computer in order to process this. But one thing that event cameras do well is that they already select the information that should be processed in the form of events that basically react to relative motion in the scene. So there are a lot of opportunities there to explore.
Okay, so I'm going to ask one audience question, actually. So one of the talks, and then we can have a more general question again. So there's a question from Almaz Zinalayev to Raquel, I believe. Question about DSDNet. How exactly does the trajectory sampler sample the trajectories? Does the number of trajectories depending on the situation on the road, ego velocity, other objects' velocities, etc.? If so, how do you handle varying numbers of classes for the trajectory prediction? Raquel, do you want to take a stab at that?
Sure. So thanks much for the question. I'm sorry for mispronouncing your name. Let's see. So in the paper of the DSDNet, the trajectory sampler does not depend on the scenario. And one of the reasons why, in the sense of what are the dynamic actors in the scene, it does depend of what the eco car has been doing in the past few seconds. And this is because there is a subset of things that the self-driving car can do, condition of what you have done where you are before. Now, one of the, so on one side, right, so the fact that you don't sample dependent on the scene, it means that there's a lot of samples that are not realistic, right? However, there is a very fast way to actually get, get those samples out. Now, in the case, remove those samples. And I guess the question here depends whether you talk about the sampling of the planner or the sample of the I guess for every one of these scenarios, sorry, for every one of these actors. So I'm talking about right now the planning. Now you can do samples that are specific for the particular scene. The problem with this, particularly for the planner, is that you might have errors in perception. You might not sample things that are the only opportunity for you to plan a safe maneuver. So it's really typically a compromise between safety and how much you trust your inference about the scene. Okay, so it's typically a good idea to sample things, although that independent of the scene. Okay, now there is in the other papers we use different strategies, and I think there's a very, very open line of work here into how you sample good trajectories. Now you have to be also very careful because typically if you want to do something smart, the sampling process takes a very long time, and you have to do all this stuff under 100 milliseconds, including all the inference, etc. So careful with how smart you get there. But great question.
Thank you. Okay, so I think I'll ask another general question to our panel. So Marc, this actually came a few times. There's a question about data and data sets. 40 involves lots of data, and in general, a lot of progress in vision has been driven by benchmarks and data sets. So I'm curious, if including for self-driving cars, things like Kitty, that are now a few years old from Raquel's group. Do we need new data sets for 4D vision problems? Is that even the right way to think about 4D vision, especially if you have some kind of active component like with robotics? Are data sets going to drive progress from now on? And if so, what data sets do we need? Or do we need some other way of driving progress? And I'll open it up to anyone who wants to chime in.
I mean, I think we need, certainly part of what we need is some new data sets. I think it's important to drive, we've seen that the last 10 years or so easily, probably even 15, 20 years, that have really been able to drive the community and focus the community, give a way for the community to somehow measure kind of progress. And so I expect that to continue. I think those data sets are in particular good at kind of somehow highlighting some specific problems. Now, they also expire sometimes after a while. And sometimes also the data sets end up somehow biasing the field. So I think there's a delicate balance in in how to do that and how to kind of move forward with those data sets. Like for example, with Kitty, I think it did some amazing things. Nowadays, there's sometimes people that use it to demonstrate that deep learning is, for example, can do visual odometry. But Kitty is in essence kind of a data set where there's a strong correlation between motion and between scene and motion, making it a much simpler problem than the generic problem of solving visual odometry with deep learning, for example. So sometimes there's kind of issues like this that pop up with data sets that I recognized because they address some problems, but then they sometimes get used in other context, sometimes the wrong context. So I think we still need data sets. I think, for example, I'm looking forward to do some of those action recognition data sets, and very cute. And to have new action recognition data sets, especially this egocentric vision in general tasks, to kind of highlight these new problems and get people to work on it. with HoloLens, I actually also hope to just make it available, like this research one, as a platform for people. You know, and I think platforms will be important going forward, to go beyond just data sets, to make platforms available where people can work on and test on and so on. So I think in robotics, in mixed reality, in self-driving, this would be very powerful. Partially, of course, in robotics and so on, you probably want, you know, partially synthetic platforms to avoid too much damage.
Thank you. Sorry, I should have managed. We might have a cameo from kids here. And yeah, sorry, Raquel, did you want to say something?
Yeah, cool. So I actually agree with Marc in the praise and criticism in terms of data sets. I think, you know, a data set really, a well-done data set drives the field. And I think it's very, very important to really think deeply into what are the tasks, because suddenly there is hundreds of researchers that are going to be working on this thing, right? So it's an incredible opportunity to really, also you have access, say, to industry, right? To really teach the field into what are the problems that matter, right? So I think that's great. I think in the case, you know, and I agree with Marc that for odometry, obviously the problem of self-driving is a very constrained problem compared to just the general odometry. Now, I think in self-driving, you know, Kitty is incredible that it's still alive, to be honest, right? We collected it, you know, 10 years ago, so it's amazing. And there's been now, you know, a myriad of different data sets, right, done by almost every company out there. But they are still very similar data sets. So it's not really bringing us to that next level. And that's, you know, what we are hoping to bridge the gap soon. But we are in need of the next big open question for self-driving, definitely.
I would also like to add something to what has been said, which is, I mean, for tasks that involve state estimation, so visual odometry SLAM, as well as segmentation, and depth estimation and so on, basically data sets are sufficient, but for other decision making and control, where actually visual feedback is needed in order to make a decision about what the next steps, then data sets are not enough. But you need actually simulators. So I think, for example, the Carla simulator for self-driving car is, in my opinion, actually a very good step in that direction. There is also the embodied AI dataset from Facebook, although it allows only a limited, discrete set of decisions to be made. But for example, in robotics, now there are a lot of simulators. I mean, Gazebo still remains the most used simulator. The point, though, is to make the simulator, is to actually release benchmarks that work within the simulator. So, for example, if you want to benchmark all the path planning algorithms, basically we should release a benchmark experiments that will allow everyone to be able to reproduce exactly the same initial conditions. This is missing. It is completely missing. So I would like that the robotics is actually spend a little bit of time in this.
Okay, thank you. So we are almost out of time. I think we'll go a couple minutes over because I'd like to get to one more audience question. Let's see. So we have Aditya Prakash who asked, what are the main challenges introduced when relaxing the IID assumption and moving towards long horizon sequential decision tasks involving 3D vision, for instance, self-driving cars? And I think this is for general answers if anyone has any opinions about this. And again, I have another audience member here with me.
Let's have Davide answer this one first.
Can you, honestly, I didn't understand the question. Can you repeat it?
It's also in the Q&A under the answered column because I typed in a question.
I see.
What are the main challenges introduced when relaxing the IID assumption and moving towards long horizon sequential decision tasks involving 3D vision, for instance, for self-driving? Sorry, does that, if the question isn't clear, we can also, I think Zoom allows you to answer offline by typing answers. But if anyone wants to take a stab at that.
You know, maybe I can take a step. Sorry, Davide, for putting you on the spot. Let's see. So there is many, I guess, complexities into, you know, going towards, you know, sequential decision tasks. And for self-driving, typically the horizon is not as long as you might think. A typical planner looks between 5 to 10 seconds into the future, right? So, you know, some of the complexities are in terms of, you know, the complexity of looking at all possible decisions that you might want to take. And what is also very important for self-driving is not just about the decisions that you might want to take, but also how those decisions might affect actually the scene as you go into the future. And that interplay and the complexity, you know, the computational complexity of these two things together is one of the, I guess, main challenges. And also the fact that, you know, again, for safety is very important, and it's important that you don't overestimate how much the others can react to you, and at the same time, you don't think that everybody will not react to you because you will never move. Right? So it's a very, very complicated intricacy between, you know, maybe a mental model of every actor is one way to actually try to tackle this, but it's definitely non-trivial. And you know, talking, sorry, and pointing out to what Davide said before, right? So, and you know, my comment about new data sets, our self-driving data sets are a loop, apart from Carla, right? So we need large-scale data sets that are closed loop, which means that you need a simulator on the loop, right? And that they are realistic. And that's the bit, right? Such that the problem that you're working on are also the problem that, you know, that technology can translate to the fleet.
Okay, any other thoughts on that? So I think we're over time. I apologize for the shortness of the panel, but if other people have questions, I think, you know, panelists can answer. There's a way to answer it online. You know, since we're a little over time, I think I'll just end there. Thank you so much to our panelists, Marc, Raquel, and Davide. I'm going to clap for everybody because I don't think that's easy to do. For the audience, I'll clap on behalf of everybody, and thank you on behalf of all of our attendees. And thank you everyone who attended. That closes the session. There'll be a second session, I believe, starting in 6 hours at 10 p.m. UK time. So yeah, some more great content there. So thanks everyone for attending. Thanks to our speakers.
Thank you.
Thank you. Thanks for organizing us.
See you guys.
See you on the flip side.
Bye.
Bye-bye.
Bye. Bye-bye.